Thank you very much to everyone who has supported me and this channel over the last 2 years. The KiCad and STM32 tutorial video you see here has reached nearly 1 million views, which is amazing, so thanks again. As has become somewhat of a ritual on this channel, this new extended video you are watching right now will guide you through KiCad version 6 this time, and how to create a simple but complete STM32-based hardware design from project creation through to getting your PCBs manufactured and assembled. Some of you may recognize this as the Udemy KiCad version 6 course, which it is, and I have as of now decided to make it free of charge so that a larger audience can hopefully benefit from the information. The earnings from the Udemy course to date have covered my development costs, so thank you to everyone who gave generously. This course is still available on Udemy under the title Learn KiCad version 6 and STM32 hardware design for anyone that would like to receive a certificate. If you would like to up your hardware design skills and support me and this channel even further, I would encourage you to sign up to my Mixed Signal Hardware Design with KiCad version 6 course, which you can find under this link fils-lab-shop.federvale.education. This course goes into far greater detail into both hardware and PCB design. Finally, and as usual, thank you very much to JLC PCB for sponsoring this video. Without further ado, let's get started. Welcome to this course on STM32 hardware design with KiCad version 6. Before we get started, I'd like to take you through a couple points. First of all, what you'll learn in this course. Secondly, who this course is for. Then a bit about me, your instructor, and finally what hardware we will be designing. In this course, you'll learn how to use KiCad version 6, all the way from creating a new project to getting your project finalized and manufactured. We'll learn how to draw schematics, do the layout, and route a printed circuit board, or PCB for short. We'll learn how to create STM32-based hardware using STM32 microcontrollers, or MCUs. We'll learn how to move away from Arduino-based designs, and also how to get your product manufactured and assembled. This course is for hobbyists, engineering students, and pretty much anyone who is interested in hardware design. People also wanting to move away from using Arduino as modules, and people wanting to make something more professional will benefit hugely from this course. Finally, people just interested in learning how to use KiCad version 6 will benefit, of course, as well. Just a bit about me. I'm a graduate of the University of Cambridge, which is a top 3 university in the world, where I studied electrical and electronic engineering. I'm a professional hardware design engineer, designing complex printed circuit boards and hardware. I also run the Phil's Lab YouTube channel, where I create educational engineering videos. Here are some example STM32 designs, and by taking this course, this will enable you to start designing something like this for yourself. All of these designs feature an STM32 microcontroller of various powers, as you can see here, and here, interfacing with USB, SD cards, codecs, ADCs, DACs, much more. In this course, you'll learn the basics of how to create a very simple STM32-based design, which you can apply to many other projects. So let's get started. We'll be basing our design very loosely on this STM32 Blue Pill, which is a very common alternative to the Arduino boards and can be actually programmed using the Arduino IDE. The Blue Pill itself is flawed in a couple ways, and we'll try to improve on it, and I'll guide you through all the way from project creation to getting our own version of the Blue Pill produced. I'll be using JLC PCB to produce the boards and also the parts available in the JLC PCB parts library, but don't worry, I will guide you through step by step. So let's move over to KiCad and get started. I strongly encourage you to follow along step by step and pause the video when necessary. So the first step would be to actually download KiCad. If you go to KiCad.org, click on download, it's available for Mac, Windows and Linux. Once you have KiCad installed, click File, New Project, and give your project a name. The first thing we always start with a PCB design is drawing the schematic, or capturing the schematic as it's called. So click on Schematic Editor. The Schematic Editor presents you with a blank schematic page. I can hold the middle mouse button to move the page around, middle mouse in and out to zoom, right click gives me some options, click and hold left to select. I have various toolbars at the top and the right here, and we'll start with these toolbars on the right. The first thing we need to do is place our schematic symbols, or our components, on the schematic, and then connect them up. Because we are designing a sort of Blue Pill variant, we want to start with the absolute essentials, and the essentials, or the main piece of this board, being the STM32 microcontroller.
And since we're almost making a copy of this blue pill, I'm choosing the microcontroller that's written over here. It's an STM32, which is the brand of microcontroller, and then these characters at the end, so the F103C86, tell me a bit more about the microcontroller. STM32s come in various flavors, and they are typically denoted by these first two characters. So there's an F series, a G series, H, and so on. And 1 indicates some sort of power. So an STM32F1 is less powerful than an STM32F4, which in turn is less powerful than an STM32F7. The remaining characters will tell you about the package size, so how many pins this IC might have, what flash and RAM memory it might have. But for the moment, I'll leave that as an exercise to you to see what other alternatives there would be to this STM32 microcontroller. We're just going to stick with this, so I'm going to copy the name, move back to KiCad, and click over here on the right to add symbol. This will load my symbol library. Once the symbol library has loaded, you can see a variety of KiCad standard symbols. So you can choose things, for example, diodes, various other devices, CPUs, connectors, and so forth. We're just going to search for the STM32 microcontroller. If I remove a few characters, you can see it pops up here as STM32F103C8TX. X essentially is a placeholder because you might have C8T6, C8T4, and so on. So double click, and then left click again to place it somewhere central on your schematic. Again, using the middle mouse button to move around, and middle mouse button or the scroll wheel to zoom in. I can press escape to cancel any KiCad command. What I typically do is align this reference designator, this U question mark, to the top, and the name of my component to the bottom here. I can double click on the name and then change it to C8T6 to give it the exact part number. This is how I would typically start with an STM32 design, or a very simple one, is start with your main centerpiece and then connect everything up that this MCU requires, or this microcontroller requires. You can see there are a variety of different pins organized in various sections. At the top we have these power pins, VBAT, VDD, and VDDA, and we'll go through what those mean. We have various configuration pins, and reset, boot 0. Then we have all of these pin banks, so PA and PB, PC and PD, and we also have these ground pins, typically denoted as VSS or VSSA. Of course, if we just place this on a PCB, this will not work. We'll have no connections and no interfaces. So what we need to do is sensibly configure this device electrically, that is, tie it to various supply or power rails, connect it to crystal oscillators, connect it to connectors, to make this thing useful. The first thing I always start with is by placing my ground and power. To do that in KiCad, go to the right and click on Add Power Port. If I scroll through, you can see I have various different power rails, I have various different flags. But what we want, if I go to the filter section, is click on GND, which is my ground. So ground is my common reference, and I'll just place it down here. And what I like to do, because this symbol is very obvious that this is ground, I can hover over and press E, and then hide the value, which is hide this ground label, and click OK. And to me, this is obvious that this is ground, and every other circuit designer will know that this is ground. Of course, if you have maybe different grounds in your system, for like analog and digital ground, should you do such a thing, it makes sense to keep those labels. But for typical systems where you just have one ground, it's perfectly fine to hide that net label. Next, we need to connect this ground up to the VSS pins. So hover over one part of the pin, click W, and click again to route up the pin. And I'll just do that, and I don't have to repress W. The W command, the Y command is active. Press escape when you're done. What you can see here, I've used one ground symbol to tie all of these VSS and VSSA pins together. I could have also, by pressing C and Ctrl V, copied loads of these ground symbols and tied these up. But you can see that's going to be pretty messy. So the way it is, if you have grouped banks of ground or power, use one ground symbol and connect these up. VSS is the supply or the ground supply, ground reference for the digital side, and VSSA is the ground reference for the analog side. So this microcontroller might include things such as analog to digital converters or digital to analog converters. In a general case, you want to keep VSSA and VSSS tied to the same ground. There are, of course, exceptions to that rule, but in 99% of all cases, this is what you want to do. So now we have our ground connections. We also need to connect our power up here. This is slightly more involved. We have a few different pins. VDD is our main supply source for this microcontroller. And I believe for this microcontroller that can go anywhere from 2.7 to about 3.6 or 3.3 volts. For STM32 microcontrollers, unless I have very good reason to do otherwise, I typically use 3.3 volts. So go again on the power port and look for plus 3.3 volts. Here we go, double click, and you can place that. You can see that my label is floating up a bit. I can hover over and press M to move my label down a bit. Now the VBAT pin can be used if we're using the real-time clock of this device, or if we have an additional external battery connected. In this case we won't, therefore I will just tie my VBAT to my VDD, which is at 3.3 volts. So again, W, and then root all of this together. Now we're at a stage where we've connected up power and ground, at least to quite a few of the pins. We need to think about decoupling. Decoupling capacitors are capacitors that will later be placed very close to the integrated circuit, to this microcontroller, and provide small local energy storages. For example, when this MCU switches and it needs quick transients of current, it can't get that just from the power supply because it goes through long leads, for example, and cables, and has quite a lot of inductance. By placing decoupling capacitors close to that device, and we'll see in detail how we do that later, we can help this device out when it requires quick switching transients. The way we do that is go up here to add symbol, type in C for capacitor, double click, and then we can place 1, and we can change its value by double clicking here. You will want one 100 nanofarad capacitor per VBAT and per VDD pin. The way I do that is move my power pin up here and connect it like this. By connecting it directly here, rather than having these decoupling capacitors floating, it enables me to see, okay, later when I come to layout and routing, that these capacitors need to tie to these pins. I can press C to copy, Control V to place, and of course, one 100 nanofarad decoupling capacitor per VDD and per VBAT pin. What I also typically like to do is place a bulk decoupling capacitor somewhere close to the IC. So I'll place another decoupling capacitor and change its value, for example, to 10 microfarads. So this bulk decoupling capacitor should just be close to the IC and will provide bulk decoupling. It's not strictly required, but good practice. And then I'm using the W or Y command, again, I link these up. The other side of the decoupling capacitors have to be tied to ground. So I can just copy my ground symbol and pop it over here. Again, using one ground and the Y command to connect everything up. This makes my schematic look a bit neater. You can see all of the relevant decoupling capacitors are right where they should be at those pins. Again, one 100 nanofarad decoupling capacitor per pin and one bulk decoupling capacitor for the whole IC. You can see we haven't connected the VDDA pin yet, and the VDDA pin, such as the VSSA pin, is for the analog sections of this microcontroller, so the ADCs, DACs, and so forth. We can perform some additional filtering because the analog supply is typically more sensitive, and the way we do that is I'll place one 10 nanofarad capacitor and one 1 microfarad capacitor in parallel. And the reason for me doing that is because of ST Microelectronics recommendations, and I'll just link that up as I did before. And I will give this a net name, which is different to 3.3 volts, which is 3.3 volt A meaning analog. Again, making sure everything's nice and tidy. And now we have to connect this rail up to 3.3 volts somehow. And again, I said this is because we want to do some additional filtering. Filtering can be done via resistor, an inductor, or ferrite bead. A ferrite bead essentially behaves resistive, dissipates heat at high frequencies. So let's use that. So if I type in bead, I can get my ferrite bead, R to rotate, and I'll just place it somewhere over here. Then connect that up, and on the other side of this ferrite bead, I will place another 1 microfarad decoupling capacitor. I can't forget my ground. And to make it clear that we've somewhat separated the analog and digital supplies, I place my grounds like so. Then of course we have to feed this 3.3 volts somehow, and that's coming from the digital 3.3 volt rail. So we have this decoupling capacitor or filtering capacitor, a ferrite bead, and these parallel capacitors feeding into the VDDA pin. And this kind of structure you will see in pretty much all of the microcontroller designs, at least for STM32 microcontrollers. Very small decoupling capacitors close to the relevant IC pins. The analog side, we might have some extra filtering. Again, this is taken from ST Microelectronics recommendations. Ferrite beads are typically given a resistance at 100 MHz, and the ferrite bead I use for this case is typically 120 ohms at 100 MHz. And I'll just denote that by 120 R meaning ohms. So we've come pretty far already. We've already placed our microcontroller, we've attached our ground and power. However, this does not mean that this microcontroller will boot up. We also have these various configuration pins, meaning N reset, boot 0, and of course the pinout of this device. Additionally, Right now we have no idea where our 3.3 volts are coming from, so we need some sort of regulator and some sort of power source. Let's first of all talk about these remaining two configuration pins. Once we have those set up and a power source, this will pretty much ensure that this microcontroller boots up as we expect it to. The N reset pin, or the reset with inverted logic pin, as this N denotes, if this pin is pulled low, this will put this microcontroller into reset mode. Typically, this N reset pin is pulled high to make sure this microcontroller runs the software or the program that's flashed to it. This N reset pin actually contains an internal pull-up resistor, so we can leave this floating. You can, of course, attach an external tactile switch to perform a manual reset, or connect this up to some sort of I/O pin. What I typically like to do if I don't use this N reset pin is just attach a 100 nanofarad decoupling capacitor to the N reset line to prevent spurious resets. So I typically take a 100 nanofarad decoupling capacitor and connect it there. Now it is good practice to expose this N reset line, but typically you won't need it very much unless you want to perform a manual reset. In other cases, you can pretty much just remove power and apply power again. Now, even though I will be leaving this essentially just connected via capacitor and using the internal N reset pull-up resistor, I still want to give this net or this wire a name. Because once we go to routing and laying out the PCB, if we don't give this a name, this will simply be called something like U1 pad 7 or something like that. And that's very hard to read or know what this pin does. So the way to do that is go overwrite, add net label, and call it N reset. Just place that anywhere on the line, and this makes sure this wire is called N reset and gives the PCB layouter some valuable information of what to do with this. For example, if this might be a high-speed line, the layouter might have to be more careful, and generally it's nice to know where things connect to. The second pin is the boot 0 pin. The boot 0 pin enables or disables the internal bootloader of this STM32 microcontroller. The main way of programming one of these STM32 microcontrollers is via JTAG or serial wire debug. Serial wire debug, and to program STM32 microcontrollers, you will typically need one of these ST-Link debug probes. They connect on the one side to your host computer via USB, and the other side via the serial wire debug signals to the microcontroller. This is very useful, and I definitely recommend you use this to program your STM32 microcontrollers because you can set hardware breakpoints, you can read live variables, and things you really can't do with typical Arduino devices. But if we don't want to use this ST-Link and serial wire debug or JTAG to debug this device, we can usually enable the internal bootloader of the microcontroller by pulling the boot 0 pin high, and this enables interfaces such as UART or USB or I2C to be able to program this microcontroller. And in our case, this is something we might want to do. Because this device supports USB, we also want to use the capability to be able to flash programs via USB to this device. So the way we would then later do this is pull boot 0 high, plug in the device, and then it'll appear as a programmable device to your host computer if you've installed the drivers. On the other hand, if you pull boot 0 low, this device, or this microcontroller, will simply run the program that is flashed to it currently. So the way we can make this boot 0 pin variable is by placing a simple switch. So again, going to the top right here to click Add Symbol, what we want is a single pole, dual throw, or SPDT switch, and it has this form. So there's a single contact on one side, and a flip between one contact here and a different contact here. This is exactly what we want. In KiCad, I can use the X and the Y keys to flip my symbol. And I'll place it somewhere over here. So on this side, I will place a series resistor, and I'll show you why in just a second. So again, add symbol, click R, and click R again to rotate. Then I can use the W or Y command to link these up. I can double click to give this a value, and I typically want a 10 kilo ohm resistor here, so 10K, M to move, and M to move the designator. So on the other side of the switch, this will then toggle between high and low. In our system, high is 3.3 volts and low is ground. You can see the default setting of the switch is by linking 1 and 2, and by default, we wish that this program runs or that the MCU just runs without going to bootloader mode. The way I'll do that is hover over, select, and click Y, so to make sure my default position is at the bottom. This is purely aesthetic, again rearranging. And then I want to tie ground to the bottom side, because in the default position, boot 0 is pulled via this 10 kilo ohm resistor down to ground, and this makes sure my program runs. And on the other side, we have simply 3.3 volts. So in this way, we've used a simple single pole double throw switch connect it through a 10 kilo ohm resistor to boot 0. You can omit this 10k resistor, but it's good practice to keep it in place. So anytime we want to program this device via USB, we simply toggle the switch manually to 3.3 volts or to the other position, program it, toggle it back to ground, and then run the program. Don't forget, we also need to add net labels to this side of the switch and to this side of the switch. You can see I've cleaned the schematic up a tiny bit, moved this and reset capacitor a bit to the left, and given myself space to add net labels. So I've added boot 0 here, and switch _ boot 0 here. You can see I've changed the size a bit, and I can double click and change the text size just to make it fit. I recommend making net labels as large as you can, except for maybe less critical net labels, for example the switch boot 0. So pretty much if we were to supply a power source here to give us 3.3 volts, this will enable this microcontroller to boot up. And this is all the required external circuitry that's actually needed to get this chip up and running. However, this is pretty boring and it won't do very much. What we actually want to do is maybe connect a crystal oscillator to help with timing. This does have an internal crystal oscillator, which isn't very accurate, so we want to add an external one. We might want to select some sort of pinout, connect UART, SPI, I2C, and so forth. The way we do that is via STM32 IDE, which is also the programming environment. I'd strongly encourage you at this point to download STM32 IDE so you can follow along. Once you have your boards in your hand and you want to program them, this is my preferred way of programming them. So this gives you an Eclipse-based IDE. You can choose the pinout, configure your device, add drivers using just this tool. So I'm going to start STM32 IDE, which I've installed on my system. Once the program has loaded, you can go to File, New, STM32 Project, at which point you'll be presented with this STM32 target selector. Here you can choose maybe if you have some sort of development board from ST, but we'll choose this MCU MPU selector. All we have to do is type in our part number, which is the STM32 F103C8, and if we see here, it's the C8TX, and again, X is a placeholder. It shows us the package, size, the flash, and RAM, how many IOs we have, the maximum frequency we can run this device at. So click on that. It tells us a bit more about it, so you can see you can operate from this supply voltage, it has USB, various peripherals, and so forth. And this is actually a pretty useful tool to select which STM32 microcontroller you might want to use. So click on Next. Then we want to give it some sort of project name, and I will just call it Udemy Course STM32 Pin Out. Of course, this project name will depend on whatever your needs are, whatever you want to name your project. All these settings are not useful for us now, and we can just click on Finish. Remember, right now we just want to do the pinout planning and we don't want to write any code for this. Once STM32 IDE has loaded the package, this is the view you'll be presented with. And this is the actual pinout, or the chip you will see from the top side. So we have the pin 1 indicator over here and the various pins around here. You'll already recognize some familiar pins, for example these VBAT, the VDD pins, VSS pins, and these are pins we've already connected up to our power supply. We of course have the boot 0 pin for our boot mode select and our N reset pin. Now there's several ways of defining the pinout for one of these devices. One way is to simply click on a pin and then choose what it's supposed to do. Another way of course is to read the datasheet or the reference manual, and I would pretty much usually advise against that unless you know what you're doing. My preferred way is going on the left here, going through various tabs and seeing what this device is capable of and what I need for my certain application. What we will be doing is making a pretty generic board. So we only want, for example, USB enabled, which will then route to a USB connector. We want a crystal enabled, which will route to a crystal oscillator. But the rest of these pins will try and just route to GPIO headers. So for us, at the moment, what we only want to select is the crystal as well as the USB connection. So if you go on the left at System Core, you can go to Sys, go to Debug, and then choose your preferred debug method. We would also want to have serial wire debug enabled, and just click on serial wire, and that enables that. And you can see this highlights PA13, which is the serial wire input-output pin, and PA14, which is the serial wire clock pin. There's also another option here, which is the trace asynchronous serial wire, and this adds a third pin, which is the SWO or trace pin. And this is very useful for monitoring and plotting live variables, but is not strictly required. So we'll stick with serial wire for now, because that reduces our pin count. Once we've enabled our debug method, I would like to go to RCC, which is the clock section, and we simply want the high-speed clock. So the low-speed clock is useful for the real-time clock, but we won't be using that. We simply want the high-speed clock to aid with our timing, for example, if we want to use protocols such as UART. So click on that, click on Crystal Ceramic Resonator, and this will enable these two pins on PD0 and PD1. Finally, we want to enable USB, which can be found on the connectivity and USB. We want to select as a device and in full speed mode. And you can see PA11 and PA12 is my USB differential pair. Later on, and just for interest's sake, you can actually go to middleware and click on USB device, and then choose a class for the USB, and this could be audio device, so to stream audio data, a virtual COM port, so a serial port, device firmware upgrade, and so forth. So nicely enough, ST has provided several drivers that gets you going with USB as quickly as you can. Also later, once you have your finished boards in your hands, you want to set up the clock, and this is done in this tab. Here you can choose your crystal input frequency and what your processor should run at. You can actually let STM32 select all this for you, given a certain input frequency and given a desired main frequency. So what we need to do now, and if you maybe later want to choose things as UART, you can also choose that here. You want to transfer this pin out over to KiCad. And that's pretty much one-to-one and very straightforward. So I want to transfer my serial wire debug, my clock pins, and my USB pins for now. And of course, this will depend on your final application. So back in KiCad, I have, for example, PD0 and PD1, which were my oscillator in and oscillator out for the HSE, for the high-speed external crystal. I can go and click and give them net names. So I'll just give them HSE in and HSE out. So let me just transfer the remaining pins from STM32 and here we go, that's pretty much it. You can see I've got my crystal over here, I have my serial wire debug connections over here, and I have my USB differential pair over here. Now we have to note for USB, or generally if we have differential pairs in KiCad, later when we come to the routing stage, we have to route them as differential pairs. The way KiCad recognizes differential pairs is via this minus and this plus, and the same name before that. So the name is USB_D, and then we have this minus and plus appended to this. This lets KiCad know that this is a differential pair, and it should be routed as such. So it's no good, of course, just having the net labels. We actually have to connect these to something. So let's start off with the crystal. Crystals typically come in 4-pin packages. If I go over here, choose symbol again, I will type in crystal, and I want to choose GND24. And this is the typical package you will need for a crystal. Of course, there's 2-pin packages, but a lot of crystal SMD packages will have these connections. So pins 2 and 4 will be ground, and this will be typically the casing of the crystal, and 1 and 3 will be the crystal in and outs. And of course, they're interchangeable. So I click on that and place it somewhere down here. On this note, a very, very useful document provided by ST is the application note AN2867 on Oscillator Design Guide for STM32 microcontrollers. If we scroll down to page 11, you can see the microcontroller and the relevant crystal oscillator circuitry. The microcontroller itself contains an inverter as a sort of amplifier and a feedback resistor to form part of the oscillating circuitry. Externally, we have our crystal, which has some sort of stray capacitance, which we cannot control, unfortunately, or at least to a certain extent, which due to PCB routing and traces, we require these 2 load capacitors on either sides, and sometimes we require this feed resistor to limit distortion and overdriving the crystal. In most cases, you can get away without using this feed resistor, and in many designs you will not see this. However, you will definitely require these load capacitors. And these load capacitors will be equal in value and will depend on the relevant crystal you choose. If I look at my parts library, I just search for 16 MHz crystal, and for example, this one here. This is a 4-pin package, as the one we just saw in the symbol, and I typically go with a 16 MHz crystal oscillator. If we look at STM32 the clock configuration panel is actually quite interesting because we can see our allowed ranges of our high-speed external crystal input. And you can see here, it's a bit hard to see, it is from 4 to 16 MHz. I have standard crystals I use, and this is one of them, and I typically go with a 60 MHz crystal. What's important to see is this load capacitance, which is rated as 10 picofarads, and of course also the package, which we'll come to later. But for us now, 10 picofarads is important because this lets us calculate the load capacitance required next to this crystal. So let me first of all denote that this is a 16 MHz crystal. I just type that in like so. Again, making sure your schematic is nice and neat. Then this side, we can route to HSE out, and this side, we can route to HSE in. Again, pins 1 and 3 you can flip, it doesn't really matter. Ground, of course, on pins 2 and 4 should be connected to ground. And this is the kind of circuitry we saw in the ST application note. We have our oscillator input and output, we are omitting this feed resistor because it's typically not required. We have our crystal, and we have these two load capacitors. So this is exactly what I've brought over to KiCad, connected my pins 2 and 4 to ground, and I have these load capacitors. Now the question is, what are the values of these load capacitors? And a typical rule of thumb is to take the load capacitance of the crystal itself, and we saw that from the datasheet or from the part description, that this was 10 picofarads. We subtract from that the stray capacitance, which is typically something like 3 to 5 picofarads, and multiply that difference by 2. So we have 10 picofarads of load capacitance. I will assume a maximum stray capacitance of 5 picofarads. So 10 minus 5 is 5. Multiply that number by 2, and it gives us 10 picofarads. And remember, both of my load capacitances will be equal. And that's a very simple and straightforward way of calculating this load capacitance. Now, of course, there's far more complicated ways of doing this and far more advanced, but for me, this has typically worked for these devices. So that's the crystal circuitry pretty much done. We then want to move over to the USB circuitry and attach a USB connector. We can do that again, as usual, by adding a symbol, searching for USB, and we have various different connectors here. I know USB-C is all the rave these days, but I prefer USB micro, so I'll place one of those. Again, pressing Y and X to flip it however it should be, and I'll place it somewhat in line with my USB pins over here. Then I can simply root out with W and so. So here I have my USB differential pair connected to my USB connector. Of course I need to connect ground. Because this is a device only, you want to leave the shield of the USB connector floating. So I can press Q, and that places a do not connect flag to this pin, and this will be useful later when we run our electrical rules check, essentially when KiCad is checking have we made any obvious mistakes in our schematic. The same thing we want to do with the ID pin. The ID pin is pretty much only used for USB on the go when we're switching between host and device modes. So again, hover over and press Q. Now VBus we'll actually be using as our power input. And the USB rail typically comes in at about 5 volts nominally, but can drop down to about 4.5 volts. And we'll simply give this a net name of VBus. So again, add power port, type in VBus, and place it somewhere down here. And this will then feed our regulator, which will then give us the 3.3 volts we require. But for now, this is pretty much all we need for the USB circuitry, or is it? Again, and as usual, application notes, especially by the manufacturers themselves, are your friend, typically. There's also another one by ST called AN4879, and that's the USB hardware and PCB guidelines for STM32 microcontrollers. If we scroll down page 3, we see we are using an STM32F1 microcontroller, and it tells us if we need any sort of series termination resistors, pull-up resistors, and so forth. Usually for STM32 microcontrollers, you do not need them. However, the F1 and the F3 series have special cases. So if I look here, we are using an STM32F103, and we're looking at the column of embedded pull-up resistor on the USB D+ line, and we need to go to the footnote. The footnote says we need to pull up the USB D+ line to a voltage between 3 and 3.6 volts with a 1.5K resistor. This is to make sure the device is actually being detected as a USB 2.0 full-speed device. So simply, if we left this circuit like this, USB would not work. The way we can fix that is again going to add symbol, click R to add a resistor, and we want to add that to the USB D+ line. So pop it down here, wire down to the USB D+ line. On the other side of the resistor, remember it has to be between 3 and 3.6 volts. So I add my 3.3 volts over here. Then double click to change the value to 1.5K, and you can see I'm not typing 1.5, I'm typing 1K5. 1.5, if I just put that down, the dot can be very hard to see. So 1K5 makes it far more obvious that this is a 1.5 kilo ohm resistor. There we go, and this should make the USB system work. Now we need a little header for our serial wire debug connections. So I go here, type in con, and you can see these various different types of connectors. There's male, female, generic, there's these various numbers. We want a 1 column and 4 row connector, and we want a male connector because this will be essentially a header. So I'll choose con01, so for 1 column, 4 rows, male, click OK, and I can put that down somewhere here. Again, using Y and X to flip however I need it. Now for the debug connectors, it's very useful to also put power and ground on them. And with any connector, you typically want power and ground connectors as well, so that's what I'm doing. And then just routing my serial wire debug, for example, down here, and my serial wire clock signal like so. You can see this is a very crude implementation of STM32 microcontroller, but very simple and very kind of breadboard and hobbyist friendly, so to speak. There are special adapters, especially for serial wire debug connectors, that make it more friendly to use with a serial wire debug probe, but this will make it accessible to most. I've also omitted any sort of filtering or ESD protection on this because this is a very simple introduction to KiCad and a very simple introduction to STM32 hardware design. By no means this is a best practices for ESD or EMI or EMC, so please be aware of that. But this will get you up and running in most cases. Also note that STM32 microcontrollers oftentimes have internal ESD protection, and that's given in the datasheet as well. This is the foundation of our circuitry. Of course, we still have to add our power supply and maybe route out some of these pins to relevant GPIO headers. So let me just centralize this a bit more. I can click, drag, and then press M to move this whole section. What I want to add is now a linear regulator, not a switching regulator, because this is a very low power system. We're not really concerned about efficiency, and we want something that just works quickly. The regulator I will be using, and is a very standard regulator, it's far overkill for this design because it can provide up to an amp of current, but it has a fairly low dropout voltage, and it gives us a 3.3 fixed output for a pretty high input voltage range. So this is the AMS 1117-3.3, and if I take that over to KiCad, again, clicking add symbol, typing in AMS 1117, and choosing the -3.3 variant, which is the 3.3 volt variant. I'll put that somewhere over here, and this is my power supply section, and we'll section off the schematic and make it look a bit nicer once we've finished it with it. Linear regulators always require input and output capacitors for stability. And a quick look at the AMS 1117 datasheet, going to page 4, we can see under the stability that we require at least 22 microfarad capacitors on the output at least, and always add on the input a similar size capacitor to make sure this device is stable and functions well. And these are called bypass or decoupling capacitors as well. So I can copy a capacitor, change it to 22 microfarads, and place it next to the device. Then I need to hook up ground, like so. At the input of my device, I'll have my V-bus over here, and at the output, I'll have my 3.3 volts over here. Now, USB power rails, so coming from the V-bus line, are typically very noisy, and it's good practice to perform some additional filtering, because this capacitor won't do next to nothing, in terms of a farad bead, inductor, or so forth. For this very simple example, and because this design will work even without filtering, we'll just leave it as it is. The regulator itself will have some sort of noise suppression, so this will do for this circuitry, but it's always advised when you're using USB, at least to power your device, to perform some additional filtering. For the sake of time, and because this simply just worked, we'll stick with this. What's also very useful, especially for test designs, is to place a power on LED. So once this regulator has fired up and producing 3.3 volts, we want to somehow indicate that to the user. We can go again to add part, type in LED, place the LED, pressing R to rotate, and we're placing that at our output rail, which is 3.3 volts. I can just indicate on the schematic that this is, for example, a red LED, and a red LED typically has a forward voltage of about 1.8 volts, so the voltage drop across this will typically, at nominal currents, a couple of milliamps, will be 1.8 volts. Now we need a current limiting resistor, otherwise this LED will burn out. So place a resistor in series, hook that up to the cathode, and to ground on the other side. I typically use resistors on the order of a kiloohm, if not higher. That gives me about a milliamp of current through this LED, and that's bright enough for debug purposes for this SMD LEDs. Because we're already using a 1.5 kiloohm resistor, I don't really want to use a 1 kiloohm resistor. I can just use another 1.5 kiloohm resistor to reduce the size of my bill of materials. So this way I only have, a couple of capacitors I need, a couple of resistors of the same value to make things nice and easy. Remember, of course, to add net labels. So even though this looks like it should have a name, it doesn't, and this is the power LED cathode. And so I've just added a small net label, and this will help us out when we're routing and laying out the PCB later. So now we have our microcontroller circuitry. This will go up and running. We have our power supply input coming from the USB micro B connector, going into our linear regulator, and giving us some sort of status LED. What's left to do is then simply break out some of these connections from these pin banks to some headers. Now I won't do all of them, and it would be good practice to do that, and I strongly encourage you to try that out for yourself. But I'm just going to break out a couple just to show you the principle of how you might do that. So let me just go back to STM32 Cube IDE and just choose, for example, 2 peripherals. I'll just go to Pinout and Configuration again. I'll go to UART, for example, UART1, click on Asynchronous, and I can actually Control-click on the pins if I want to change the pin out. And you can see I don't really like that the PA9, PA10 pins are so close to the USB. So I can control click and see where else I can place them. And you can see the flashing black pin and go over there, click UART1TX, and it moves my UART over here, which is a nicer location. So I have UART enabled, and I might want, for example, an I2C. So let me go to I2C1, click I2C, and it's placed it directly over here. Let's see if I can move that somewhere else. I can try I2C2, and I2C2 might be somewhere over here. So let me just move that over here and get rid of I2C1. So in this way, I've just enabled two peripherals, just to show you this is how you would do it for your scenario if you need I2C, SPI, and so forth. So I have I2C and UART over here. Let me just transfer that over to KiCad. So here you can see I've transferred over my UART pins and my I2C pins. And before we continue, we have all of these unused pins, and for STM32 microcontrollers, this really isn't a problem leaving them floating. Again, in KiCad, what I want to do is press Q, and then I can also press Insert on my keyboard, and this will add the same thing or the same command I just did, for example, this no connect flag, to the pins below. And I can just fill in all of these pins with no connect. So let me just do that. And here we go. Now all of the unused pins have these no connect flags, and this is good practice to make sure you don't have that many ERC or electrical rules checked warnings. So what we want to do is maybe reuse this connector we're using over here to interface with our UART and our I2C. So we can simply copy this connector, again pressing Y and X to kind of rotate it around, and then route that out to UART and I2C. So here I have my UART signals, and again I want to place power and ground as much as I can on my connectors, like so. Same thing for I2C, but also keep in mind that I2C requires pull-up resistors, and it's typically a good idea to keep these on the host side. In this case, the microcontroller will be the I2C host typically. Now for 3.3 volts, and even if I want to do something like I2C high speed or at about 400 kilohertz, I typically use 2.2 kilo ohm resistors. Because I have these 1.5 kilo ohm resistors, I'll just go with 1.5 kilo ohms to be honest. There's no real harm even going low as 1 kilo ohm. Try to stick around 2.2 kilo ohms. So you can see here I have my I2C clock and data lines, and they each have their individual and own pull-up resistors of about 2 kilo ohms, 2.2 kilo ohms, up to 3.3 volts. And on my connector, which is a male connector, I have 3.3 volts and ground. Typically for every signal pin you want at least one ground or at least one reference, but for these very simple designs, this will do. Okay, and that is pretty much all we need for this very, very simple STM32-based schematic. We have all the decoupling capacitors, all the various configuration pins, a high-speed external crystal, some connections broken out, USB with the required pull-up resistor, and we have our linear regulator to give us our 3.3 volt supply, as well as this status LED. So the next step, we're actually going to clean this up a bit, draw some bounding boxes, add some notes, and make this just a bit more professional before we move on to PCB layout and routing. Now, although this schematic might look kind of alright and function pretty much properly, it doesn't look too great though, does it? What we want to do is section our schematics into readable parts. This is because we might know what's going on, but we might not know in a year or two, or if someone else wants to proofread our schematic. If someone gave me this schematic, I wouldn't be too happy, to be honest. I want it sectioned. For example, this is the power supply, this is the microcontroller. Give me some notes, maybe how did I come up with these 10 picofarad capacitors? Why is this 1.5 kilo ohm resistor here? And who maybe even made this schematic? What are the titles and so forth? So let's add that. First of all, let's section some things. And the way you can do that is by using this Add Connected Graphic Lines tool over here. And I'll just draw some bounding boxes. Now it doesn't have to be too pretty, just a rough indication of what components belong together. So now I've drawn bounding boxes around my main parts, that is my regulator circuitry and my microcontroller circuitry. What I then need to add is some text boxes to tell the user what these are. Click on Add Text and just say this is the power supply, put that over here, and this is the microcontroller circuitry and USB circuitry. Of course, I can make this a tiny bit bigger by double-clicking, increasing the text size, and maybe making it bold. Then, of course, I would like to give this whole page sort of a title, and this is very important when you do multi-schematic pages. Again, place some sort of text, and I'll just call this the Udemy STM32 Demo PCB. And I'm sure you can come up with a much better name than I can. And that, of course, should have the largest size. Before we annotate the schematic with some more comments, for example, why these resistors are here, why we chose these values, and so forth, let's just quickly do this, what is called a title block down here. The way we do that in KiCad is go to this button over here, And then we can change our paper size, orientation, issue date, and so forth. I'll just copy over the date. I'll say this is my revision 0.1. The title is the Udemy STM32 demo PCB company. I'll just do Phil's lab and any other comments that might be useful of a website or so forth. Okay, and this you can see down here is filled in at the bottom and just makes it more professional, more easier to use, especially if you have multi-page schematics. Okay, so let me just add some minor comments. I can do that by clicking the text again and just annotating, telling the user or the person that reads the schematic what is really important and why I made certain design choices. This will help also with layout and routing. Okay, so I've added some small text just to help people out. For example, over here I've said, VBus, it looks like where's this even coming from? I'm telling the people this is coming from a USB connector and is normally at plus 5 volts. I also require a minimum of 22 microfarad input-output capacitors, input and output over here, as well as one 100 nanofarad capacitor per pin, how I calculated the load capacitance for this crystal, what application nodes are important, that this is a VDA filter, and that I used STM32 IDE to make the pinout. And this is just, of course, an example, but it's incredibly important that you keep this, as well as labeling net names, adding these kind of little hints to the person who reads the schematic. This will really help you out with even more complicated designs. So once you've cleaned up the schematic a bit, the next step is then to actually annotate the designators. So you can see here, I have all of these question marks everywhere. So I have C question mark, U question mark, and so forth. And what we want is to give these proper numbers. So for example, C1, C2, C3, C4. Same thing with my ICs, LEDs, resistors, and so forth. This is required because, well, first of all, for placement, for the program to know that this schematic symbol matches over with this PCB footprint. For assembly, we need to know, okay, where do we put C1? Where do we put C4? What value does C4 have? So the way we do that is either manually by double-clicking, typing in C1, C2, and so forth, or we can let KiCad do that for us. So the way to do that is go up here in the toolbar and click in Fill in Schematic Symbol Reference Designators. We can say which schematic sheets we want to do, how we want them sorted, and so forth. So you can simply click Annotate, close that, and see how KiCad has done it for us. This isn't always the greatest, and it depends on the alignment of your schematic. So here, C1, C2, but then C3 is jumped down over here. And this is because of the settings we used in the designator. So we can do by sort symbols by Y position, click Annotate again. And because of the alignment again, here I have C1 starting here, even though I want C1 starting here. So oftentimes, if I'm quite honest, I will just do this manually because I have my preferred way of sorting my schematics and the way I think is logical. So let me just do that. So now I've briefly gone through and annotated my designators. So I start over here, C1, C2, C3, C4, and then move down. So first of all, kind of section by section, and then top to bottom. Same thing with resistors, connectors, and so forth. So the next thing we have to do before we can move over to PCB layout is actually assign footprints to these symbols. So the symbols are the entities that live on the schematic, and footprints are entities that correspond to these symbols that live on the PCB. So we'll have certain dimensions, for example, for this regulator, we'll have certain pad sizes, and we want to link that symbol with the corresponding footprint. But before that, we also have to do the electrical rules check, just to check for sanity our schematic. So you can go over here on the top and click Run ERC. And you can see, luckily, we only get one error. And you can see this is something to do with a power flag error. So because this symbol is defined that VDDA is a power input, and we haven't really defined what 3.3 volt A is, it could be an output, it could be an input, KiCad is complaining. The way we can solve that and tell, okay, this is actually a power source, effectively it is, because we're getting power from here, filtering it a bit, and it's still pretty much a power source. The way we can get rid of that is by placing something known as this power flag. Power flags you can find in these power ports. You type in flag, it's the first thing that comes up here, and this lets KiCad know, or the electrical rules checker know, that this is a power source. So we can go again, press the ERC button, click Run, and we have 0 errors and 0 warnings, so that's pretty good. Before you move on to the next stage, you should thoroughly check your pinouts. You should check that these parts are even available to buy, that you know where to source them, that these connections are correct, that the component values are correct, and so forth. So thoroughly check your schematic before you move on. But now let's move on to assigning our footprints. So now we're ready to assign footprints that correspond to our relevant schematic symbols. The way to do that in KiCad version 6 is go up here to the Run Footprint Assignment tool. You can see on the left we have various footprint libraries that already come as standard with KiCad, and of course you can create your own footprints or download them from the internet. We'll just be using the standard KiCad footprints today for simplicity and because we don't really need anything else. So we want to turn on these filters and turn off this one here. Essentially I'm just filtering by which library this component will require and the number of pads this component has. So the way to do that is then go through your symbols over here in this list, and this is listed all of the symbols we have in our schematic. And on the right, we can choose the relevant footprint. Typically, I will try to stick with 0402 or 0603 size SMD components. For larger value capacitors or something that requires higher power handling, I will of course go larger. So 22 microfarads, I might go with something like an 0805 capacitor. I can double click to assign that. 10 microfarads, that's pretty big. I'll always go with an 0603. 100 nanofarads is pretty small, and a standard package for that is 0402. And these footprint sizes are something you just get familiar with. It also depends if you want to hand solder, what your PCB manufacturing assembly house is capable of, and so forth. But these sizes are pretty much safe, even for hand soldering. So I'll just go through and select the various components. The LEDs, I might want to have a larger 0603. Ferrite bead, I will also go with an 0603. And connectors are a very, very big subject to talk about and a topic for a whole course, to be honest. You will typically have your standard or favorite connectors, and I'll leave that up to you which one you want to choose. I will just choose connectors I'm very familiar with, this Viewer to USB Micro B. For these connectors, I will simply use these 2.54mm pitch vertical headers, and if you scroll down, going to pin header, you can see this vertical over here. I can also, if I want to inspect the footprint, click over here, and then also go to the 3D viewer to show me what this footprint actually looks like with the 3D model. This is very useful just to double check. So let me choose those. And for resistors, I will just always go with 0402. At least if I don't have very high power handling requirements. Again, switches are a huge topic in itself. Just choose one you're comfortable with or have the footprint for. Lastly, for the crystal, again, we want the SMD32-based package. And this we got over here from the package. This is a standard SMD package for crystals. It's the 3225 4-pin package. So just select that here, and you can see for the AMS1117 and for the STM32 microcontroller, KiCad has already had the relevant footprint selected because it was linked with the symbol. So once you're happy, click Apply and Save, and click OK. Now we have all of our symbols linked with relevant footprints, and we can move over to the PCB layout and routing. So now that we've assigned our footprints to our finished schematic, we can move over to PCB layout and routing. The way to do that is then go on this button on the top here in KiCad, click Open PCB in Board Editor. And this is the view you'll be presented with, and initially if you haven't seen something like this before, it might be a bit daunting, but we'll go through step by step how to set up our PCB, our board, and then do the layout and routing. The first thing with any PCB design is to set up your board stack up, so what layers you'll be using. Will you be making a 2, a 4, 6 or more layer board? Will you be having power planes and so on? For this design, a 2-layer board is more than sufficient. So to set up your board in KiCad, go to this button at the top left here, and then you'll see this view, and we'll go through these tabs on the left here. The first tab is the board editor. So this tells us various layers. So we have a fabrication layer, which might be used for assembly. We have a paste layer to print the solder, paste for soldering, silkscreen, which is essentially the text on the front and the bottom, solder mask to prevent solder bridging, and our main layers of interest for us at the moment are the front and back copper layers. As I said, we will be making a 2-layer board. Typically with a 2-layer board, you'll keep the top layer as a signal and the bottom layer as a solid ground plane. So anytime we need ground, we can use what's called a via, which is a plated through hole, to dig down to the bottom layer from the top layer and connect to our solid ground plane. Indicate this by choosing power plane from a bottom copper layer. The rest we can pretty much leave the same. If we go to physical stack up, we won't go into much detail, but we can see we have 2 copper layers, which is what we want. And this is the actual stack up of the PCB going from top to bottom. So we have the text and images, whatever you want on the top, called the silkscreen, paste layer, mask, copper. Then we have this dielectric material, which is typically fiberglass FR4, bottom copper, and the same as we had on the top. We won't mess with this, but our typical board thickness will be about 1.6 millimeters. We can choose the board finish, which is the copper finish, and typically you don't need to specify this here. You can choose gold, which is immersion nickel gold. You can choose hot air surface leveling, but we'll come to that later when we actually get these boards produced. What's very important with PCB designs is setting up your design rules. Design rules are there to help you fit and ensure that the board is manufacturable. If we go, for example, to a PCB manufacturer, for example, JLC PCB and any other PCB manufacturer will have this, they'll have some sort of capability section. In the capabilities section, they will tell you, okay, what tolerances do they have on their board thicknesses? What are the minimum drill holes or maximum drill holes you can use? What are clearances you can use? So track to track, pad to pad, hole to hole, and so forth. And depending on which standard you're designing to or which manufacturer you'll be choosing, you'll have to copy these capabilities into KiCad. So these design rules you can put in over here, for example, these constraints. So we have, for example, a minimum clearance between copper items, track widths, annular widths, via diameters, and so forth. So what I'm going to do is just transfer this over from JLC PCB. So once you've filled in all these variables, all these constraints from your preferred board manufacturer or standard you're designing to, we can go over to predefined sizes. And in KiCad, the way we route is we predefine track sizes, so track width, so it might be 0.3 millimeters, 0.4 millimeters, via sizes of different holes, and if we need them, differential pairs. I typically have two standard sizes for my tracks, one being 0.3 millimeters for signals, so I'll type that in here, clicking the plus button, and 0.5 millimeters when I route my power. Of course, if you have controlled impedance, traces, or if you need any other specific trace widths, you can just add them here. For vias, I have a standard via size, which is the pad diameter is 0.7 millimeters, and the hole diameter is 0.3 millimeters. And this will serve you well in most scenarios. Now we will need differential pairs because remember we have USB differential pair, the data differential pair, and we'll have to add a differential pair. Now you might have heard of something of controlled impedance, but we won't be dealing with this in this board. Essentially because our design is so simple, our speeds are so slow, we can get away with using pretty much any differential pair dimension for a USB trace, assuming we keep that USB trace or these USB traces as short as we can. So I will just go with a typical trace width of 0.3 millimeters with a gap of 0.3 and a via gap of slightly larger of 0.5. And we can just start with that and see if that fits our needs. Once you're done with that, you can keep the rest of these settings as pretty much standard. For more complicated designs, I urge you to go into far greater detail, but for this will do. Now that we've set up our track widths, you can see them in the top left here. We have two defined tracks. We have a typical via size, and here we have the grid settings, which we'll be using a lot in just a second. On the right side here, we have our various layers. We can hide and show layers by clicking on this eye symbol, and we can select which layers we want to plot on. So for the next step, we're ready to import all of our components via the footprint import tool, and then move over to layout. So now let's import our components, our footprints, linked to the schematic into our PCB layout editor. We can do that by going to the top here and clicking on Update PCB with changes made to the schematic. And you'll see this dialog box come up, which adds all of these footprints to your PCB. Click on Update PCB, close, and you can see we have these groups, which are all the footprints we selected from the schematic on our PCB. So let me just put them somewhere down here. Now what we start with, and typically what we start with a PCB design, is our very, very rough layout. So we'll make little islands of components, for example, all the microcontroller section together, all the connector sections together, regulator sections together, and so forth. For this, I typically use a larger grid size, for example, 1 millimeter or 0.5 millimeter, just to move things around. What's also very useful is by pressing Alt 3, or by clicking View, 3D Viewer, we can see what our board already looks like. And you can see KiCad is already complaining that we don't have a board outline because we haven't defined that yet. So once we start placing our components properly, we can define some sort of board outline, add some mounting holes, and then do the routing afterwards. So back in the 2D view, what I'll do is I'll hide the fabrication layers, the top fab and bottom fab, and this cleans things up a bit. Let me start with the most important sections first. So I'll click on my microcontroller and press M to move it around. And I'll just move it in its own little section. Doesn't really matter where to begin with. What's really useful now is when you have two monitors or split screen is to have the schematic on one side and the PCB editor on the other side. For example, like this. So every time I then click on a component, you can see on the PCB layout editor, in the schematic editor, this jumps to that component. This is really good to see, okay, what connects to what. It also works the other way around. So if I click on C6, in my PCB layout editor, it jumps on the other side. So what I want to do is start with my microcontroller, start with the most important parts first, and to me, the most important parts are the decoupling capacitors and this crystal oscillator. So let me do the decoupling capacitors first, starting from pin 1 and C4. So I'll take C4, which is my first small decoupling capacitor, and move over to pin 1. You can see I'm placing it fairly close to the pad of the microcontroller, but not close, for example, like this. If I look at the 3D viewer again, you can see this is pretty much almost colliding with this pin, and this is not what we want. We want to place the decoupling capacitors very close, but not too close. So something like this is absolutely fine. I can use Control-Shift-M to give my measurement tool, and this is about just under 2 millimeters. I can also just click on my silk screen, which is my labeling for my components, press M and R to rotate, and just, make it a bit neater to start with. So let me just go through all of these decoupling capacitors. So now I've placed all of my small decoupling capacitors, and you can see if I have, for example, these 3.3 volt and ground connections, I want my decoupling capacitor placed very similarly. So 3.3 volts I can later then route straight out like this, and ground I can route straight out like that. I could have, of course, placed my decoupling capacitor somewhere like this, but this increases my current loop between ground over here. So this is not a good thing to do. You want to prioritize your decoupling capacitor placement like so. The next thing we do is not place this large bulk decoupling capacitor because this simply just has to be anywhere close to the IC. What's important to me is this crystal oscillator section. So let's do that next. I can click on my crystal, press M to move, and just move over like so. And you can see with these rat's nests, what these are called, these lines here, these very hard to see lines, these will tell you, okay, these are components and connections that aren't routed yet but need to be routed. This is a very straightforward way to see where components need to go. You can see HEC in is the top, HEC out is the bottom, so I need to rotate my component, press M and R to rotate. So something like this. Remember that a good layout makes your routing life so much easier. I've already rotated this component this way because HEC in can then route underneath the crystal and into this pad here, whereas HEC out can route straight down through this. Move my silk screen to the other side, and of course I can't forget my load capacitors. So click on that. And you want to place these load capacitors in line with the traces. So I could place my load capacitors up here and another one down here, but this isn't good because you're increasing the capacitance by adding extra traces. So I'm just going to place it somewhat in line like this. I'm going to move the silk screen, and I can already see maybe I should move this back a tiny bit. Now the crystal placement isn't entirely critical, and it can be a bit further apart, definitely further than these decoupling capacitors. So as a very rough initial placement, remember we want to start with a very rough placement and then hone in, and we'll probably adjust the placement a bit when we get to the routing stage. But in this way we have our HEC in, we can route out directly through here, under the crystal into this pad here, and on the other side we have HEC out, giving us some clearance away from HEC in later, into HEC out like so. So this could be pretty neat. These pins over here belong to these decoupling capacitors, and these of course are also very important. So go to C8, and place it something like this. You can really see this might be getting a bit cramped, and it's perfectly fine to move these sections further away from the MCU, so I can shift click and press M to move the whole section. A very important part of PCB layout and design is keeping proper spacing between signals and traces. So I've placed this 10 nanofarad capacitor over here, which is C8, really close to the device. These larger capacitors, for example C9, can be a bit further away. So I'll place that somewhere over here maybe, rearrange the silk screen, and then I can do my little pi network, this filter with a farad bead and this other capacitor. Let me select that, and the placement of this isn't too critical, at least not for this simple design. So this might be an adequate layout for this design, where I have my pi filter here, consisting of the 1 microfarad capacitor, farad bead, and another 1 microfarad capacitor, and that then feeds into my 10 nanofarad capacitor, which is placed very close to my analog decoupling point at VDDA. Again, we can use the 3D viewer pressing Alt-3 and check out our layout so far. So you can see we've placed the decoupling capacitors fairly close to the relevant IC, we've placed the crystal a bit further and made sure the silk screen is nicely aligned, at least for the moment, and spread out. Nothing is overlapping. So this looks fine to start with. We've now done our most important circuitry, at least for the microcontroller first, and you should always start with proper decoupling capacitor placement and sensitive components such as the crystal oscillator over here. Then you want to move on with order of priority. So for example, these low speed signals, which are pretty much a DC, like this boot 0 and then reset, even though they are important, they're not really critical to route, and it won't change the performance very much by actually routing them rather differently. What might have an impact in performance is, of course, this USB differential pair, serial wire debug, and these various connectors over here. So let's start off with this USB and serial wire debug as our next area of priority. To do that, I can take my USB connector, so by clicking on it, pressing M to move as usual, and then using the rat's nest, you can see that it wants to go over here. So I can place it somewhere here, and you can see my differential pair comes out of pins 33 and 32, and very nicely routes directly over to my USB connector. Now, of course, I could put it closer, like this, but some distance like this is fine for this connection. Something fairly short, again, using my measuring tool, using Control-Shift-M, it's under 10 millimeters. This is perfectly fine. We don't really need to worry about impedance matching and so forth for this protocol and for this length. I can, of course, move my silk screen, Another point of moving components further away is that it's easier to assemble. If I moved this connector really close, it would be really hard to get under these pads to solder them if I'm doing, for example, manual assembly. So let me just leave it somewhere over here, and again making sure these signals are in line so I make my life a lot easier when it comes to routing later on. Once we start placing our connectors, we can actually then kind of see a board outline. So it already says here that this might be a PCB edge. We might place connectors on the outside, the switch on the outside a bit, and start forming a feeling for our PCB outline and our PCB board shape. Remember, of course, we need this 1.5 kilo ohm resistor in line, or in parallel essentially with the USB-D plus line. So let me just click on it, M to move as usual, and drag it over. There's several ways of placing this. The best way is that this is actually then sort of in line. We don't want to have some sort of stub where you have to route out like this, then up like this, and then like down like this. We want to place it in line with our connection. So when we later come to routing, we can simply route out through this pad and into the pad of the connector. Really simple. So that's how pretty straightforward our USB connection was. Of course, we have to take care of the power circuitry later, but let's do the serial wire debug first. So I can click on J3, which is my serial wire debug connector, press M to move, and again using the rat's nest to see where it needs to go, and KiCad is indirectly telling me, okay, somewhere up here. I can see the pins are serial wire clock, serial wire DIO over here. So serial wire clock means this pin over here, serial wire DIO means this pin over here, which means I need to rotate. So press M. Let me just rotate that twice. You can see by doing proper layout again and again and again, it makes my routing life later so much easier. All I have to do later is then go up here, route into serial wire clock, go out here, route into serial wire DIO. So somewhere up here as a rough placement seems to be fine. Again, adjusting the silk screen to make things nice and readable. Later on, of course, in the final stages of this design, we'll give these proper designators, so saying this is the serial wire debug connector, this is what these pins do, this is the USB connector, and so forth. But as a rough placement, this is perfectly fine to start with. So our layout is starting to take shape. Let's have a look at it in the 3D viewer to see if there's any problems, and this is something I typically do quite a lot while I route and lay out the PCB. I can already see two problems. First of all, here we are missing a 3D model for this connector, and this is important if we're designing enclosures or doing kind of sanity checks if everything's fitting, and also if the footprint is correct for the connector itself. Secondly, you can see this dip switch we use for the boot 0 pin is the footprint that is huge in comparison to the rest of the components. So let's fix these two little things, first of all by changing the footprint of this switch over here. We can do that pretty easily. We can go into the schematic, go to the problematic part, double click on it, and then go to this footprint selection here, click on this button, and then we can change the footprint to something that is maybe slightly smaller. So I've gone and chosen this switch over here, which is far smaller and also an SMD style switch. We can look at the 3D model, and luckily there's also one in place, and this looks fairly reasonable for now. So I'll just double click on this to select it, click OK, and then back in my PCB layout editor, I can again go to the Update PCB with Changes Made to Schematic button, click Update PCB, and you can see my switch 1, the one we wanted to change, has now changed, and I can see that in the 3D viewer again. This is much more suitable for this design. It's far smaller, far more reasonable for the switch and the purpose we want it for. So we've fixed our switch for now. We also want to add a 3D model to this connector. The way I typically do that is I either go to the manufacturer's page, and they usually have 3D models available for download. So you simply have to get the part number. So in this case, you can just double click and then get the part number, which is this one here, and look at the Virt homepage, which will then lead you to this page. Usually they're on the download section, and you can see here we have CAD files, including the relevant step file. So we'll download that now, and I've simply placed that in the course folder, so in my project folder. Then back in KiCad, I can double click on my footprint over here, go to 3D models, delete the one which it can't find, and then add my 3D model. So I go to this little folder icon over here, go to available paths, and go to my relevant project directory, click on my step file, click OK, and there we go. It's placed it on the model, but you can see it's not aligned properly. So what we can do is not change the scale, because the scale should be 1:1, hopefully, unless we've messed something up with the model or with the footprint. We want to change offsets and rotation. So let me just adjust that using these commands on the left here. So by a bit of trial and error, I can see I need an Y offset of 1 and a Z offset of 1, and that places my pads nicely on the component pads over here. I'm checking the 3D model that it's nice and aligned, not interfering. Also the holes aren't interfering with anything. So that looks good. Once you're happy, press OK, and now we can go back to the 3D viewer. And we can see our 3D model has now been added. So that's really good. And that's how you would fix things like these 3D models. So we fixed the switch size, and we've also fixed our 3D model for the USB connector. Now we can continue again with placement. So now that we've fixed our models, we can now move over to laying out the remaining parts of the board. For example, this boot 0 connection, so I can click on the resistor that's in series with my boot 0 pin, and move it again using the rat's nest to somewhere where it needs to be, which seems to be somewhere up here. Then the switch we've just adjusted, I can press M to move. I will place it somewhere up here just for now. And then I can slowly fine-tune my layout, moving my connector positions where I think they might be by the end of it. Remember, we want to do a rough layout first and kind of hone in to our final layout. Then we still have these connectors over here before we need to do the power supply. And we can't, of course, forget this bypass capacitor for the N reset line. And this is going to be a bit cramped because we have the HS-in connections up here and reset over there. But N reset isn't that critical, and it doesn't have to be placed anywhere close. So what I'm thinking, I'm going to place it somewhere down here because I can simply then later route out over here, down here, and into the N reset line here, for example. Then we need our 2 connectors. So I have my UART connector over here, again using the rat's nest to guide me. That seems to be somewhere up here as well. Just checking the orientations. If I left the orientation like this, you can see these paths will cross, so I have to rotate like so. And then I can just adjust things around. I can move the boot 0 switch over here maybe, 0Y debug connections over here like so, and make sure the silk screen doesn't overlap. For example, like this. You can also see what's nice with these connectors rotated like this is that I have my ground and 3.3 volts always on the same sides like so. So that makes sense. Now I have my I2C connector. Click on this in the schematic, and again, do the same thing as usual. Move it down here, rotate it so it makes sense. And of course, I can't forget my pull-up resistors. So R4 and R5, if I click on them, move them over, and as with the USB pull-up, I want these in line with my I2C connections. For example, like so, and like so. What we can already see here is because we'll be routing our 3.3 volts, we'll not be using a dedicated power plane, these will have to make some sort of jump like this. It will be later, and again, I want to help myself out when I'm coming to the routing stage, move these that the 3.3 volts are facing each other. And this will make my routing life just a tiny bit easier because I won't have to jump that much. So there we go, I can do something like this. So I can come up with SCL over here, into my pin up here, and SDA the same way down here into this pin, and these 3.3 volts I can then join up a bit more easily. So the rough layout is starting to take place. All we need now is the power circuitry. So lastly, we have to lay out this power supply section over here, which includes the LDO regulator, the 2 capacitors at its side, and of course our on LED. Again, because we've sectioned the schematic quite nicely, we know which sections we have to lay out together, for example, by using this bounding box. So I can click on my regulator, move that over, and you can see my power input will be coming from this USB connector, which is pin 1, and nicely, we then know, okay, our regulator or power circuitry should probably be somewhere close to that pin, so it's nice and in line and makes our routing life easier. I'm just going to rotate this package so my VBus can be routed nicely into this USB connector. Then I want to place my bypass or decoupling capacitors, and those should be close to the relevant pins of the regulator. So they shouldn't be floating somewhere over here or somewhere like this. You want to consider both the forward and return paths, so VBus as well as the ground connection. So something like this should probably be okay for the input capacitor and the output capacitor. The same rules apply. I want to keep my paths short between my capacitors and whatever circuitry they're connecting to. So something like this, so I have my 3.3 volt connection here, ground over here, for example. And then I can simply route my VBus out down later, like so. I've just adjusted this in, just move this whole island in a bit, again narrowing down and honing in my layout to make this a tiny bit more compact. And then of course I have my power on LED. You can click on that. And the placement of this really is not critical at all. But I'll just place it close to where it should be, so maybe next to this output of the regulator. And of course the relevant current limiting resistor in line with it as well. So something like this seems perfectly fine. And later we'll add some labels to tell the user what this LED is actually useful for. You can see I have one last component floating around here. And if you remember back, this is the bulk decoupling capacitor for the microcontroller. And this, as I said before, can be anywhere close to the relevant IC package. Because our power source is here, the kind of furthest distance away is somewhere up here, so this is typically where I'll place my bulk decoupling. So if I just rearrange this a tiny bit, I will probably put it somewhere up here, like so. And here we go. This is how we've arrived at a pretty rough layout using the schematic as a guide and doing section by section and then moving those sections together. Again, I can use a 3D viewer Alt-3 to view my layout. And you can see it's not ideal because, okay, this USB connector should be hanging off the edge a tiny bit. I need to do my edge cuts layer, my PCB layout a bit more properly, and I can make this a bit neater with all these connections. We also have to add mounting holes, so let's do that in the next step. Then narrow in on our layout, adjust the connector positions, and make sure we have a really nice and neat layout before we start with routing. So we want to add some mounting holes in case we want to put this in sort of enclosure or something. The way to do that in KiCad is go back to the schematic page, click on Add Symbol, and look for mounting hole. You can either choose just a simple mounting hole or also a mounting hole with a pad, for example, if you want to tie that mounting hole pad to ground, and that can be useful for oscilloscope probes and so forth, but we'll just stick to a normal mounting hole with no electrical connection. So I'll place 4 of these and then choose the footprint. If I double click on it, I can choose the footprint like so, navigate to the mounting hole tab over here, and then choose my footprint. I'll typically choose standardized footprints and screw sizes, for example M2 or M3. Because this is a pretty small board, I'll just go with M2 for now. Click OK, and then I can just copy these another 3 times and draw a bounding box around them. And so this is what I've done. Because I've selected my footprint for one first and then copied it, all of these mounting holes will have the same footprint, being an M2 hole. Again, I've drawn a bounding box, given them a title, and indicated what mounting hole types these are. This is good practice for these schematics. So now we can save and go back to our PCB editor and then import those changes as usual. And you can see I now have 4 mounting holes, which I'll place at the 4 corners of my board. So pretty roughly, I'll just select one, place it over here, the second one, place it over here, third one over here, and a fourth one somewhere over here. Now you can see these are not aligned, and what you can do is change the grid size, or double click and place them in the relevant position you want, and make sure they have a nice spacing. So let me just do that now, and then I'll discuss it with you afterwards. So here I've now placed the mounting holes in pretty good distances. So meaning that I have whole number distances. So for example, 35 millimeters in the X direction and 25 millimeters in the Y direction. And this will help the mechanical team out a lot. To do so, I've had to move the components around a bit. So for example, I've moved J2 and J3, these headers, up here at the top. I've moved the switch for the boot mode select pin somewhere over here. And I've brought everything kind of more central. I've had to move, of course, some silkscreen around as well. Just make things neat. Now, silkscreen for holes you don't really need, so let's get rid of that. The way to do that is double click on the relevant silkscreen, and I'll just move it to the fabrication layer. And I'll do that for all 4. We also don't need the silkscreen, for example, J2 and J3, J1, J4. I'd rather place silkscreen that actually tells us more about what these connectors do. For example, this one is the UART connector, or this one's the serial wire debug connector, or this is a USB connector. So again, let's get rid of the silkscreen. So something like this should be fine. Again, using the 3D viewer to check. This looks okay. So what we can do now is define the board outline. And the way we do that is by going to the edge cuts layer over here on the right, clicking next to it, and then using the draw line tool. So I'll try to go out a specific distance away from this mounting hole, let's say maybe 3 millimeters. Remember, we want to give the screw head some sort of space, and this is indicated by this pattern outside here. So 3 millimeters seems to be okay. Let me just draw lines outside. So now you can see I've drawn 4 lines, 2 horizontal and 2 vertical at the sides of the PCB that I want. I haven't closed them up yet because I would like to make rounded corners. You can also see we might have to move the connectors around a bit to make sure it looks nice with the board, but that happens with iterations and when fine-tuning this design. First of all, let's make some round corners. Again, staying on the edge cuts layer, choosing the draw an arc tool, clicking on the center of a mounting hole, going on one side of the arc, and then drawing to the other one. And there we go, we've made a rounded corner, and I'll just do that for the remaining 3. And here we go, I've filled in the remaining corners, and we can now, because we have joined up this edge cuts layer, press Alt-3, and we should see our new board outline like so. So pretty nice, we have a defined board outline which has some proper dimensions, proper distances between mounting holes, and rounded corners. So now we want to maybe move these connectors out a bit to make sure they actually fit with this board. So let me just do that now. I'll just grab my USB connector and just move it out until PCB edge is approximately lined with the actual PCB edge. This we can move out a bit as well, just to make sure this tip of this switch shows out a tiny bit. What we also need to do is, because silkscreen can't be printed, of course, on an empty PCB, or if there's no PCB material, we have to remove this silkscreen. So double click on the component, click Edit Footprint, and this will just edit this one instance of the footprint. We go to silkscreen and remove the silkscreen over here, like so. Save, close, and this has now removed the silkscreen here. We can press Alt-3 to view this in 3D, and we can see we have no overlapping silkscreen. and the tip of this switch is showing out just a tiny bit to make it easier to flick. And then we just move these connectors out just a tiny bit as well. Not too close to the board edge, but not too far away either. And same with the bottom side, and maybe more in line with these I2C pins. And there we go, we finished a very rough layout of our board. We've added mounting holes and the edge cuts layer to define our PCB outline. Next, we can move out to fine tuning and then actually routing this board. So let's do that. So now that we have a pretty rough layout finished and we fine tuned it a tiny bit, it's time to start with routing. Remember, we had already defined certain track widths and we'll be using 0.3mm for signals and 0.5mm for power. And we'll just use a standard type of via. As with layout, when it comes to routing, we want to route the most important or critical traces first. So for example, the decoupling capacitor connections, the connection from and to the USB connector, and so forth. For a two-layer board, I typically like to start with just placing a ground plane on the bottom, so a whole copper plane tied to the ground net to provide a stable, low impedance reference for all the signals on top. So if I go and click next to the bottom copper layer, click on this icon here called Add a Filled Zone, and I'm just going to draw a filled zone, and KiCad will then automatically fill in depending on the shape of the edge cuts layer. So starting at the top left, once I add a copper zone, I need to choose which net, so I'll filter for ground, and I want it on the bottom copper layer, and I want a certain clearance. 0.5 is pretty large, so I'll go with 0.3mm clearance and a minimum width of 0.25. Pad connections, so for example, these through-hole connections I want as thermal reliefs with 0.5mm relief gap and 0.5mm spoke width, and this helps with soldering. The fill type is a solid fill, and that's all we need to select. Click OK, and then draw your outline. Like so, like so, and then finally close that up like this. You can then press B to re-pour, and you can see on the bottom layer I now have a filled zone. I can click on these buttons on the left here to change my zone visibility to help with the routing. So in the 3D viewer, we can then turn around the PCB and we can see we have this ground plane here with these thermal reliefs every time we have a ground connection to a through-hole pad. So this is how I typically start, and then this is really nice because every time I have a ground connection, for example here, I can route out and simply drop a via down, which is this plated through-hole connection down to the bottom layer, and this gives me a nice low impedance connection, the ground plane. More of that later. Let's start off with routing the critical connections first. Because I want to do my signals and critical connections first and my big power traces later, I will start by using this 0.3mm track width. So select that, and then I can either go on the right here and click Route Tracks, or click X, and this will start my track routing process. Now, of course, I want to route my tracks on the top, at least to start with. So click on the top layer, and let's start routing. Starting with these decoupling capacitors over here, I can hover over the pad, click X, and as soon as I come out of the pad, I want to go left, give myself the maximum spacing, because I'm going to be doing the same thing on the right pad over here. So coming out, giving myself spacing, and routing into the pad. So you can see this way, as soon as I come out and as soon as I have the space, I am making the space. I don't want to route straight out like this, because I will have, not for these signals, but for many signals I have crosstalk and noise problems. So always maintain proper spacing. And as you can see, because we did proper layout of our capacitors, it's been really easy to route this out. Then from these pads, I can choose a slightly wider track width. And for decoupling capacitors, I want to make these as wide as I can. Again, doing the same principles, routing into the pad like so. So fairly symmetrical. Here, because I'm limited by these pad widths, I have to use the track width that is the same as the pad width into my capacitor like so, and I will do that for the remaining capacitors. So I've done exactly the same connections for all of these remaining decoupling capacitors around this MCU. We'll do the ground vias a bit later. For now, let's just do traces. So the next important section might be this crystal over here, so let's move over to that. And the same rules apply. Again, routing a track. Going on my HEC out, as soon as I can, I try to go down into HEC out and then into my crystal like so. Then the same thing on the top on HEC in. As soon as I can go out, I want to go up like so. This gives me the maximum spacing between these two fairly sensitive lines, and then I can route underneath the crystal into my HEC in. There we go. We'll do the ground connections later, as I said. So this is really simple. The main thing you have to maintain is proper spacing, and when you can, try to break away from sensitive signals and traces. So my recommendation is to do sensitive circuitry first, and that includes decoupling capacitors, and then we can move on to doing USB and the various other peripherals before we then do the power sections. So now let's move over to the USB differential pair. For two-layer boards, it's pretty difficult to route USB according to the specifications, so maintaining a controlled impedance and so forth. So that's why we have to keep this distance fairly short, but we'll get away with this. The way to route a differential pair, because we've told KiCad that with this D+ and D- net labels that this is a differential pair, we simply have to go to root differential pair, click on one end of the differential pair and it'll route out like so. And because of my placement, I can simply route straight into my USB connector. So this is pretty neat. Because I've aligned my USB connector and the USB differential pair pins perfectly with my IC of the microcontroller, we can just draw pretty much like a straight pair of lines. Also, you can see R3, which is this pull-up resistor, is placed in line with the D+ line. So I could even move it in just a tiny bit. There we go. So the pad isn't causing much of an obstruction or obstruction to the differential pair. So that's how easy that is. Then we can route the kind of less critical signals. So for example, we have the serial wire clock signal, serial wire DIO, going to our serial wire header up here. So again, I'll be using my 0.3mm track width, clicking X or clicking this button on the top right, simply routing out of the pad and into my serial wire clock pin like so. You can see because of this decoupling capacitor, my serial wire debug can't go out here, but nicely enough, I can just go behind it like so and underneath the microcontroller, and this is absolutely fine to do like so. Of course, you might adjust the layout and routing later, but as a first guess, this is probably fine. We can move on to this connector, which is the UART, as well as this boot 0 connector. On the note here, remember we labeled up net labels, so everything has a nice net label and you can see what do these pads mean and where do they need to connect to. So going with my UART, as soon as I come out, I'm breaking away, giving myself enough clearance, thinking ahead, okay, where are my other traces going to run? Because my UART RX is going to run like so, I'm still keeping clearance and routing out like so. I'm keeping clearance because I still have my boot 0 pin here, which goes essentially straight out like so, and then into this resistor, and from the resistor into the switch. Again, I'm breaking out as soon as I can, giving myself nice, good spacing between these traces. And I can even make that even more by deleting some of the traces and just doing it again. And in this way, you'd kind of fine-tune your layout, make sure you have adequate spacing, if you can, of course. In some designs, the layout might be a bit more cramped. Then on the bottom side, we of course have the I2C, and we'll do exactly the same thing as we did just now. So if I try to route I2C, I can do this with this SDA trace over here, but with the SEL trace, I'm having problems. And this is because of my clearance constraints. I have to move this capacitor slightly to the right. So I could maybe lay out my capacitor a bit to the right like this. This is still absolutely fine. And it enables me to do a better layout job of the SDA line. And again, with the SCL line, as soon as I can, give myself spacing and route out like so, for example, and then from these pull-up resistors into the connector pins. So again, using the 3D viewer to check a bit, I've slightly optimized the layout so the pull-up resistors route directly into the traces, for example, like so. And we've actually pretty much routed all of our signal pins. What now is left to do is route, power, and connect all of the ground up. So let's do that. So now we're ready to connect up ground and power. And remember, because we have this large ground plane on the bottom layer, connecting up ground is actually really easy on this 2-layer board. All we have to do is, for example, if we have a ground pad, such as one over here, is take a very wide trace, that is a 0.5mm trace. On the front layer, use the track tool, clicking X, routing out a tiny bit, and pressing V to then dig down. We don't want to bring the via too close to the pad because that will give problems with via sucking in solder, so I have soldering problems. So something like this distance, fairly short, is pretty good. Again, we can look at that in 3D and see this seems fair enough. So let me just do that with all of the other ground vias, and you can try that out for yourself. When it comes to ground connections, for example, if I have ground connections here, I don't really want to route out ground here and do a via down to the ground plane, and then also do a route out here and a via to the ground plane. This will cause something known as ground loops. What you want to do is then prefer this ground pin, the one of the MCU, route it out at the required width, and drop a via here, and then use this as a single via connection. Also forgot to mention that we need to route out and reset, of course, but let's place the vias first. You can see how I've placed this ground via. I didn't place it further up because I want to route and reset out, and I want to have space to do that. And so by pre-planning my vias, I can do that. So out through here, and into my end reset capacitor, for example. Remember also not to place holes on any silkscreen because that is simply not manufacturable. Maybe if the vias are tented, that is, they're covered with solder mask, but I always try to not place any holes in pads or any silkscreen, for example. So now I've hooked up all of my ground vias, well, almost all of them. I've left the ones on this power supply out because I want to place quite a lot of ground vias and then use a copper pour or a copper fill to connect them up. So let me place my ground vias first. for example, like so a fair amount, about 1 or 2 per pad. And then I again go in my top copper layer, click on add a filled zone and start it somewhere up here. Again, filtering for ground. Clearance I will use as 0.3mm, minimum width of 0.25. And this time, because I'm using SMD connections, I prefer to do solid pads. Now, if you have copper imbalances, you have a lot of copper on one side of a component and a very small amount of copper on a different side, you might get problems with thermal imbalances, which could cause tombstonings, so improper soldering of components. But for these, I really haven't had a problem, so I'll do solid. And I'll simply trace out a copper pore to connect all of these ground connections up. And this could look like something like this, for example. If I turn on this view, you can see I now have a copper pore, and I like to call these power puddles. And these will help with connectivity and lowering the inductance. Look at that in 3D as usual. You can see it'll look something like this, all of these power components connected nicely together. And I'll do the same thing with my V-bus, as well as my 3.3 volts. So now in the same way as we've just seen, I've added power puddles to 3.3 volts and V-bus to the input from my USB source, which is my USB power source from the connector. This is typically how I would route out at least this regulator section using these large power planes, so to speak. Once we've done that, we can then route out the 3.3 volts taken from the output side, so this output capacitor of this linear regulator, using again very thick traces to all over the board. So as I've shown here, from the output capacitor of my regulator, I'm going out, for example, my LED, routing these very wide traces to various parts of my circuitry all over the board. Remember to keep clearance between power puddles, traces, and components as usual. Now, this might seem fairly thin at 0.5mm, but this can even carry up to about 2 amps or so, with only about a 10-degree temperature rise, and we're using the couple of tens or hundreds of milliamps on this board, so more than sufficient. Now, anytime I need to, for example, jump traces, the way I would do that is route out, for example, my power, press V, route on the bottom side, and come up with another via. And you can see I've kept this path, where I'm cutting up my ground plane underneath, very, very short, and as short as I can, of course, maintaining proper clearance between traces and vias, and pressing B to re-pour, and you can see I've made a small cut on my ground plane. And I don't want to do very many of these, so I'm going to minimize the number of jumps I have to do, and when I have to do a jump, I'm going to minimize the distance. What you can also see, I'm using slightly larger vias, so the KiCad default vias for my power, and this is typically good practice, especially if you're going into higher current designs. And there we go, I've now finished routing these 3.3 volt rails. You can see it's perfectly fine to route this for this lower speed designs, and make sure you do the smallest amount of jumps as possible. So for example here as well, I'm pretty close to the board edge, and you wouldn't want to go any closer. But for this is fine, at least I didn't have to cut the ground plane. Once you're done, press B again to re-pour, and then check everything out in the 3D viewer, like so. And you can see, also right-angled corners are absolutely fine, and don't let people tell you otherwise. And there we go. So there we've finished our very crude routing and layout of a very simple PCB. And if we ship this off now, producing the manufacturing files, this would work. So what we want to do next is actually make this a bit neater, add some silkscreen, and then produce the manufacturing files. So the way you can add silkscreen is go to the silkscreen layer, for example, the top silkscreen, then add, for example, text. So I might want to indicate that this is the serial wire debug connector. Typically, line widths and heights of a minimum of 1mm. I would typically go a bit larger, maybe 1.25, and a stroke width or thickness of 0.2. And I can place that close to my relevant connector. Maybe place one over here to indicate this is UART. And then do the same for all the connectors around and all of the switches. So I've added a bit of silkscreen now. You can see I've labeled what the connectors are and do. Maybe also positions of switches. For example, if I move this switch into this position, it means my bootloader goes to 1 and is high, indicating maybe where ground is on which pins and so forth. Also what the LED does and so on. On the back side, maybe the month and year I was doing this and what revision number this is of this board. Of course, you could indicate much more, for example, your website and so forth, what these individual pins are. That's very good practice, but for the sake of time, we won't do that. Also important that you see that silkscreen isn't on holes. So for example, this C12, I would have to move a bit. Let me do that because we have a silkscreen on a hole. So I'll just move that to here. And these are the kind of checks you would have to do now. You have to make sure that your schematic is correct, that your layout and routing is right and so forth, and also the silkscreen. Another very important step is then the design rule check. To run a design rules check, and this will check if what we entered with the manufacturer capabilities, if we have met those with our PCB, if we have any clearance constraints and so forth. You can do that by going up the top here, design rules checker, and then clicking run DRC. then hopefully we'll get 0 errors and 0 warnings. And also in the unconnected items tab, we will get that everything is routed. So this looks great. One last thing I'd like to cover before we move over to producing manufacturing files is adding a little logo to your PCB. That can be quite a nice little touch. So in KiCad, you can go to this image converter tool, which will then open up this. Click on load bitmap and load your logo. Now to determine the size, which we have to put in here, you can go back to the PCB layout editor and find some sort of free space. Use Ctrl-Shift-M to measure. And this seems to be, about 5 or 6 millimeters we have space. So I'll type about, let's say, 6 millimeters in and square. I want it as a footprint, and I want it on the front silk screen. And then I can simply export to clipboard, and then place it on my PCB like so. Again, using the 3D viewer to check, and you can see I've got my little Phil's Lab logo there. And of course you can change the size, play around with it, and then also give this board a little name. And here we have our pretty much finished board, which we can get ready for production. Because we also want this board assembled, we have to export a bill of materials. And the way to do that is go back to the schematic editor, go to the top here, and generate bill of materials for the current schematic. Click generate, and you will find this bill of materials generated here. I will just generate a manufacturing folder just to make sure all of our export design files are in there. And just move that over here. Then just give it a name. And if we open that bill of materials file, you can see we have reference designators, quantities, values, footprints, descriptions, and, for example, manufacturer part numbers. And you will have to fill in manufacturer and manufacturer part number for all of these items before you send it to your assembly house so they know which items to populate. Of course, we can get rid of stuff, for example, these mounting holes, because they're unassembled. Next, we need to generate the Gerber files, so the actual plots of all of our layers, as well as the footprint placement files. So for the pick and place machines at the manufacturer, where do they need to put these components? And we can do that in the PCB layout editor. Go to File, Fabrication Outputs, Component Placement to generate the footprint position file. I want that in CSV and millimeters. And I'll use my output directory as my manufacturing folder. Use relative path, yeah, that's fine. And there we go. Then we click Generate Position File, and we've generated our position file. And this footprint position file will look something like this. Again, giving the component designators, values, the X and Y coordinates on the PCB, the rotation, and which layer these are on. Now keep in mind this format also for the bill of materials and the footprint placement file or the component placement file will vary depending on which manufacturer you go with, but they will have detailed descriptions of how to format it for their required needs. The last thing we have to do is plot and check the Gerber files, which actually tell the PCB manufacturer how to make the PCB you require. So go to File, Fabrication Outputs, Gerbers. On the left here we can choose which layers we want to plot. We want to plot the copper, paste, silkscreen, mask, as well as the edge cuts to tell the manufacturer about the board outline. And that's pretty much all we need. Output directory is manufacturing, that's right. We don't want this generate Gerber job file, but we also want to generate the drill files. So we go to generate drill files. We want millimeters, plated through hole and non-plated through hole in a single file. Click generate drill file, close that, and then plot the Gerbers. There we go. And now in our manufacturing folder, you can see we have all of these Gerber files, and we can add these to a single zip file, which we then upload later to our manufacturer. Before we do that, however, it's good to go back to KiCad in the Gerber viewer, and then check our Gerber files before we send them off. So go to File, open Gerber plot files, manufacturing, and select all of them. And this will show you all of the Gerber files. I typically start with all of them off. I will start with the back copper layer, and this should just be pretty much our ground fill with a few small little cuts in them. So this looks okay. The mask layer, paste, silkscreen is the bottom text, so to speak. The edge cuts, which is our outline. Front copper, which is our kind of most interesting layer with the MCU, and this is how the copper will actually be deposited, or rather etched away from the board. Front mask, paste, and silkscreen. So it pays off to take some time to really check your Gerber files, check for any shorts, or anything that doesn't look right. Oftentimes you will discover some mistakes in those. But once you have those, you can go over to your PCB manufacturer to order them. So for example, a very inexpensive and good PCB manufacturer is JLC PCB, and you can just click on Quote, and you can upload your Gerber files. So you can navigate to your manufacturing folder, click on your Gerber zip archive, and let that upload. And again, you can use their Gerber viewer on any other PCB manufacturer's site to check out your Gerbers to see if they're rendered properly. Then before you order or place the order, you have to select some various options. For example, we want this to be a fiberglass PCB. It's automatically detected the layer count, which is 2 layers, the dimensions of the PCB, and here you can choose how many you want to order. Then you can choose the PCB color, maybe purple or black or something like that. and then choose the surface finish. I typically recommend to go with lead-free hot air surface leveling, or if you want something more fancy with immersion nickel gold, and for certain applications this is preferred, you can choose this option. Other than that, we want to remove the order number. Oftentimes PCB manufacturers place some sort of order number on the silkscreen, which doesn't look very nice, so I typically tick that option. And then you can also add PCB assembly, choose which side to have assembled, and then upload the bill of materials and component placement files. And that's pretty much it. Then you can place your order, and as you can see, PCBs these days don't cost very much. So that's pretty much it. Well done for making it through this course, and I hope you followed along and learned something, and I hope you can make your first STM32-based PCBs and really improve your designs. If you've enjoyed the course, please leave me some feedback at Udemy, and if you haven't already, you can check out my YouTube channel at Phil's Lab to see more PCB and electronics videos. Thanks again, and I'll see you next time.